Okay, thank you everyone. We are done with our 10-minute break and we're going to get started here again. The next presenter will be Alan Butler, who is going to take us through the beginning of the system reliability analysis. This will be an interactive type of presentation, so we'll be looking at some different types of results beyond what's included on these PowerPoint slides. And this leads to the question that we've been receiving about making this PowerPoint available after this presentation. We are recording this webinar, and the next few weeks or so we'll have this session recorded so you can follow through with some of the interactive presentations that have been going on. And that'll be available on our website in the next couple weeks. And we will have the PowerPoint that was used here available in the next week or so posted to our website. And so with that, I'm going to turn it over to Alan Butler.
All right, thanks, Carly. Now we're going to start talking through the system reliability analysis, starting with the methodology and then later on going into the results. We'll start off going over a general approach and then look at the models, the tools, and the different methods we use to perform the analysis. How we evaluated system performance, and then start looking at identifying conditions causing vulnerabilities, and finally wrapping up with how we implemented the portfolios in our modeling framework. To start, Carly showed the supply-demand figure earlier and quantified the total system imbalance, but that doesn't really speak to the entire picture. It doesn't take into account reservoir operations or reservoir storage, which is instrumental in meeting those year-to-year shortages, nor does it take into account the geographic disparity of supply and demand in any one year. And finally, we recognize the importance of many other different basin-wide resources, and we wanted to evaluate the effects of increasing demands and potential reductions in supplies on those 6 different resources categories. So we simulated the state of the system for the next 50 years for all scenarios, both with and without options and strategies, and then used metrics for 6 different resource categories to quantify the effects to those different resources. And so we looked at water deliveries, electrical power, water quality, flood control, recreational, and ecological resources, and developed metrics for each one of those resource categories. And so this map on the right shows all of the different locations that we had a metric, and the different colors indicate all the different resource categories, both in the upper and lower basins. Now we're looking at our system reliability framework. I'll start off talking through the framework kind of at a high level, and then we'll go into each one of these areas in a little bit more detail later on. To start off with, we had what we called 15 system response variables, and these are really just raw model output, things such as reservoir elevation or flow at different gauges in the basin. And at this point, they're not really tied to any resource category. However, when you look at something like Mead pool elevation, it does have a little indication of water delivery, recreation, and power resources. Then we also had 90 different reliability metrics, and these are those different metrics for the 6 different resource categories that were on the map in the previous slide. This is where we tied different variables to those particular resource categories and then identified what we called a reference value. And so this is something that was associated with the location and the particular resource category. And for example, at Lake Mead, we had a reference value of 1,000 feet, and this is the current elevation that the Southern Nevada Water Authority can no longer divert water out of Lake Mead. So this was identified as one of those 90 reliability metrics. We then moved from 90 different reliability metrics down to 27 what we called indicator metrics. And these indicator metrics were either very important reliability metrics or sort of an aggregation of multiple reliability metrics. And we kind of reduced from 90 down to 27 so that we could try and digest the effects to all different resource categories as we were looking at our simulation results. For each one of these indicator metrics, we identified what we call a vulnerability threshold, and these vulnerability thresholds were a certain point where a particularly bad outcome or when the system was particularly vulnerable. And an example of this is if Lake Mead falls below 1,000 feet just one time, that's a very unacceptable outcome, and the system is vulnerable at that point in time. For other resource categories, it might be not quite as stringent. You might need to be below a certain threshold for 2 or 3 years in a row before you're particularly vulnerable. And we calculated the vulnerabilities both as what we called a percent of years and a percentage of traces. And so any year that the vulnerability occurred was marked as vulnerable and reported as the percentage of years. And then if 1 year within a given realization was vulnerable, that was reported as the percentage of traces. For the water delivery indicator metrics, we then went through and identified the conditions that led to these vulnerabilities. And these conditions we looked at were different system conditions, things such as mean river flow or droughts that you experienced. And we calculated these conditions that typically led to a vulnerability. So for example, if the mean river flow was below 15 million acre feet, you were likely to experience mead below 1,000 at some point in time in the future. At this point in time, we brought in our different portfolios that Carly discussed into the modeling framework, and then we used what we called signposts to turn on different options within a portfolio. And the vulnerable conditions really informed our development of signposts, and the signposts were used to turn on an option in a dynamic sense that Ken will go over later on. And then finally we get to our portfolio analysis, where we start comparing how effective each of the portfolios are, and then look at some other comparisons such as the costs and the total quantity of yield that each portfolio implements. Before we go into any of the details on the metrics, we'll take a minute and talk about some of the models and tools that we used in the study. To begin with, we used the Colorado River Simulation System, or CRSS. It's our official basin-wide long-term planning model. It's implemented in Riverware, and we've used it for many different environmental impact studies and other long-term planning efforts. The figure you see on the right is what's called the geospatial view of the model. And so you can see that the model begins all the way up in the headwaters of the Green and the Colorado river basins, and then continues on down all the way to the northern international boundary with Mexico. CRSS simulates operations at 12 different reservoirs and then delivers water to over 500 different users throughout all of the 7 states. And it's a monthly time step model, and it's particularly strong at giving a wide range of potential future system conditions. It's not a deterministic model. Here you just see sort of a zoomed in figure where you can actually see the layout of the model. At this particular location, it's the Fontenelle Reservoir, and then some downstream diversions from the Green River. The next tool that was really instrumental in completing all of our modeling simulations in the time frame of the study was the Riverware Study Manager, and it really helped manage all of the input and the output for our over 240 different scenarios, and then automated the simulation process so that we could hit go and run a lot of those scenarios at once without having to start each of them individually. And so here's a figure of the study manager and all of our different inputs into CRSS. You can see the different supplies and demands and portfolios. The study manager then combines all of these different scenarios, and the left part of the graphic shows all the combinations and allows us to select which of those simulations we want to run. The study manager can also automate the generation of results, so when you move from the input into CRSS to the output, as shown in this figure, it can automate the generation of different output in Excel workbooks. Now we'll start talking through that system reliability framework, starting off with the reliability metrics. Many of those reliability metrics were directly measurable in CRSS, things such as pool elevations at reservoirs, and that thing were directly measurable in that monthly time set model. However, many of the ecological and recreational resource metrics, we needed to know daily information to evaluate those metrics. And so we have a couple of different methods that we employ to evaluate daily flows in CRSS. To start off with, for the ecological metrics, we used two main different methods. First, below the reservoirs of Navajo and Flaming Gorge, we wrote rules and different logic to mimic the daily operations of those reservoirs, but then to set the release at a monthly level in the model. With that knowledge, we could then evaluate whether or not different daily flow requirements below those reservoirs were met. The next method we used at other locations really took different flow requirements that were stated in terms of a particular flow for a certain number of days, and we took the daily gauge, USGS gauge data at these locations, and then took the average hydrograph for those locations and kind of superimposed the daily flow requirements over those daily hydrographs. And this is shown in the figure on the right, where the blue is the daily hydrograph at a location, and the red and green lines are different flow requirements. Once we've kind of added those required flows or flow targets to the daily hydrograph, we summed the daily flows into a monthly volume so that we could evaluate those flow requirements in our model. We performed something similar for our recreational resource metrics for the boating flow day metrics. These were developed with American Whitewater and Hydros Consulting, and they were really used to quantify kind of the number of days in a month that were particularly good or for boating and recreation in those different reaches. We started by having American Whitewater perform a public survey to determine different flow thresholds for acceptable or for optimal experience in those reaches. And then we worked with Hydros to develop a method to compute the number of days that were in the acceptable or optimal range. In this case, we used 30 years of historical gauge data to create different plausible flow patterns at those gauges, and converted those to kind of a unit hydrograph, and then using the monthly output from CRSS, created 30 different plausible daily hydrographs. And then we were able to count the number of days that fell in either the acceptable or the optimal ranges and report out that information. So now we're going to move to the indicator metrics within that system reliability framework, and I'm going to turn it over to Ken Nowak to go through that portion.
Thanks, Alan. So as we talked about earlier, there are 90 some odd indicator or individual metrics, which makes it pretty challenging to distill down and summarize and view the results across or even within a particular resource category. So we came up with the idea of an indicator metric, and the idea is to offer sort of a summary of the suite of statistics and metrics within each category. Shown here are different resource categories and then the number of indicator metrics developed for each one. Under water delivery, you'll see we had 6 total. 2 examples are shortage in the lower basin, and then also what we're calling a leaf area deficit. Essentially, in the case of the upper basin, when flow at leaf area over a 10-year period falls below 75 million acre feet, we determine that there's a deficit, and we report the shortfall to that 75 million total volume, and then also the frequency. And so that's one important indicator metric for upper basin water delivery. We had 3 for electric power. An example here might be upper basin total power generated. Water quality and flood control only have 1, generally because we know there are pinch points in the system where there's a bellwether, and we can just look at 1 and really get an idea as to are we looking at a vulnerable future or not. Recreation actually had 11 indicator metrics. This is for 2 reasons. One is that it tends to be a more distributed resource and harder to aggregate, but also we had multiple types of recreation. We had this idea of a boating flow day, but we also had shoreline recreation at our reservoirs. Last, the ecological metrics were summarized into 5. 2 examples here are the Yampa near Maybell and the Colorado near state line. So this is actually a summary here to show the path to metric vulnerability. How do we take an indicator metric and move to this idea of vulnerability? Effectively, there were 2 pathways, and we're going to go through each one as an example. The first is to elevate a particular metric that's of interest, that's telling, that we just want to look at in more detail. And so here we have Lake Mead falling below 1,000-foot pool elevation. That's in the water delivery category, and that's one of our system reliability metric, one of those 90s. So if we move now to this idea of an indicator metric, we simply elevate that same metric in its form and look at it as an indicator. Finally, we introduce a threshold. How frequently do you have to be below this elevation, or what is the criteria relative to that reference of 1,000 that identifies vulnerability? Well, because as Alan stated earlier, the Southern Nevada Water Authority is particularly sensitive to Lake Mead falling below 1,000. Any occurrence, so a single occurrence in our model, would flag vulnerability. Now, the second track to moving to this idea of vulnerability from a system reliability individual metric is shown here with the recreational metric category. And so if we look at boating flow days on the Yampa and then the green, we have a number of locations. And so what we did was, instead of trying to pick one and elevate it, we said let's just sum the total number of days within that Green River Basin that gave either acceptable or optimal or unacceptable boating flow days. So instead of having a maximum potential of 30 boating days, you have, if there's 5 locations here, 150. You get the idea. So now that we've moved into this aggregate view across the entire green subbasin, we need to identify some type of vulnerability. And we did that with an idea of a control run. The concept was, we're going to look at that historic resampled hydrology, but maintain demands roughly where we believe them to be now. And we get an idea of what is the availability of that resource presently, and then identify, did the future scenarios where we're looking at that aggregate number of boating flow days significantly deviate from what we believe that resource's availability is right now. So that's the second sort of approach for really quantifying and moving all the way from a metric to vulnerability. And I'll just note here that flood control and water quality were similar more so to water delivery, in that an individual metric was elevated because of its importance or significance, whereas ecological category followed more of the path of recreation, where we're developing a new indicator metric and vulnerability associated with that new indicator metric. So next here we have vulnerable conditions. And the idea here is we want to identify the conditions associated with vulnerability. We no longer want to be trying to identify some combination of supply, demand, and policy that's problematic for the system or a particular resource category, but we want to identify which traces have a common trait that seems to be problematic. And that really simplifies our effort and also makes for a more informed process of avoiding conditions that are undesirable, because if we know what we're looking for, we can better guide our policy decision making. And so for each of our water delivery indicator metrics, we looked at a variety of possible conditions that could be defining the traces that really were problematic. And the types of things we looked at were various statistics on stream flow. We looked at demands, we looked at demand trends, and we even looked at reservoir operations and tried to really hone in on 1 or 2 things that were flagging or defining the traces as vulnerable. So here we have an example analysis of identifying vulnerable conditions. And this is for the Lee Ferry deficit indicator metric. Each point on this kind of confusing graph here actually represents a single trace that we looked at. And what we see here are that the points marked in red incurred a leaf area deficit vulnerability, and those traces marked as gray did not. And so what we wanted to do was define a vulnerable space that grouped as many of those red outcomes as possible. And so on the x-axis, we have the mean flow for the driest 8-year consecutive period in each trace. And then on the y-axis, we have simply the 50-year long-term average flow of each trace. And through our analysis, we found that a high number of those vulnerable outcomes fell in the 11.2 million acre foot average flow during that 8-year drought, but also included a long-term annual flow, that 50-year average of 13.8 million acre feet or less. Now there's one more layer of detail here. You'll notice that some points are X's and some points are O's. X's are falling within the yellow space, that vulnerable space, while O's are not. So put simply, we want as many red X's, meaning it's vulnerable and it fell within our defined space as possible, and we want as many gray O's as possible, meaning we did not believe it was going to be vulnerable because it fell outside of the space, and in fact it was not. Put another way, a gray X is a false positive. We thought it would be vulnerable, but in fact it was not. And a red O is a false negative. We thought it was going to be non-vulnerable, and in fact incurred that vulnerability. So if we move forward, we'll actually look at a few summary statistics of that plot. On the right, we actually see the definition of vulnerability again. Recall that the long-term flow has a mean of 13.8 or less, and the 8-year drought has a mean of 11.2 million acre feet or less. Now, of all those traces we had plotted up, 19% were vulnerable, meaning 19% of those points on the figure were red. Now, the important thing is we want to look at our vulnerability statistics. The space we define per that definition shown right captures 78% of vulnerabilities. So 78% of the red points on that figure fell within our space. So essentially we're capturing 8 out of 10, which is a pretty good success rate. Now the other statistic you want to look at is within that space, what is your density or density of the actual vulnerable events. You could imagine if you expanded that space to be quite large, you would capture all the vulnerabilities. However, you'd also capture a lot of non-vulnerable events, and it would not be particularly meaningful. And so what we've done here is effectively balanced, capturing a high number of vulnerabilities while keeping it mostly to vulnerable traces, not unvulnerable. So why is this important? Well, we're going to go into some more detail when we actually look at results, but one more meaningful example right now is that if we know what the problem characteristics are of our traces that lead to vulnerabilities, we can start to look for them and hopefully make informed decisions in order to avoid those vulnerabilities from occurring once we start looking at portfolios and implementing options. So as an example here, the upper figure shows Lake Mead pool elevation, and the pink area is the vulnerable space. And you can see at around 2055, we actually fall down below 1,000 feet and the trace incurs vulnerability. Now, if we look at the figure below it, and we had some signpost, some condition that we had developed based on our understanding of vulnerable conditions, we can actually keep an eye out for that signpost and hopefully make some sort of a decision or action, implement an option to hopefully avoid that. And so you'll see that we have a threshold for our signpost right around 2047, and we fall below that threshold. And in our modeling sense, that would mean, okay, it's time to do something. We need to take action in order to avoid the vulnerability. And I think you'll see that that actually does, in fact, happen as we start showing our modeling results. All right, before we get to the results, though, we want to go into a little bit more detail on that process of how we model options, how we implement them, and ultimately what we get out of it. And so as Alan presented earlier, we used CRSS, our long-term planning model, and at the beginning of our simulation we input a variety of information, including option timing, meaning when is this option available, yield, how much water does it generate or how much demand does it reduce, and also cost. And so options were implemented based on cost effectiveness when a signpost occurs. So essentially, when we see that flag saying a problem is looming, let's look at our options, and of those that are available, let's implement the most cost-effective approach. The idea here is that we want to be dynamic and only implement options and make investments when they're necessary, so we're avoiding that overinvestment. And then another important note here is that while the implementation is dynamic, once an option gets put on, it remains on for the duration of the simulation, regardless of whether or not conditions or hydrology have improved appreciably. And so we use this analysis for all of our portfolios and assessed all of the different future conditions that Carly described. So just to put an example to that quick overview, we have this dynamic portfolio logic example. So our simulation is moving along, and a vulnerability flag occurs in 2022. The first step in this process is to say, has that vulnerability already been addressed? Meaning, was there a previous flag on that time step that had an option implemented that actually kills two birds with one stone? Meaning, we think that we've actually put something in place that's going to help this out. And if that's the case, we just continue the simulation and look for a vulnerability to occur in the future. But if it's not the case, we're going to start reviewing options. And let's say we review some option N. Well, we look at that option and we look at information that's associated with it. Things like timing, magnitude, and what vulnerabilities does it actually address. And so that's in fact the first question. Does it address the vulnerability that's flagged? If it doesn't help us out with regard to what we're looking to accomplish, it's a useless investment, so we're going to pass it over. If it does help with the issue at hand, we're going to continue and ask, is the option available? You can see in this example table, only one of the three options is in fact available in 2022, so we'd want to make sure that we actually have something that's not a big infrastructure project that needs another decade before it's available. So assuming that option is available, we proceed. And then there's a criteria for a minimum investment. Essentially, we want to do enough when we have a vulnerability signpost flag that we feel as though we're going to get some sort of a shift in the system and that the yield isn't so small that it's going to be unmeasurable or not really avoid going into that vulnerable space. So if it doesn't meet the minimum magnitude, we'll actually put it in place anyway, but we'll go back and look for another option through the same process we've described. If it does meet the minimum magnitude, we'll put it in place and then continue our simulation until another flag occurs or signpost, and then we'll repeat this process again, hopefully making an informed decision in terms of the options we're implementing to strategically address vulnerability in a cost-effective manner.